The 2 kg sphere is attached to right rod which rotates in the horizontal plane. So this object is moving in this plane, horizontal plane, it's not vertically, so gravity has no role to play. If the system is subject to a couple moment of m equals 0.9 t square, where t is in seconds, determine the speed of the sphere at t equals 5 seconds. Okay, so principle of angular impulse moment gives me HO1 plus m0 dt equals h02. So you're going to find the speed when the time is 5 seconds. So solve for V using that formula and then poll your answers. Yeah, I'll stop at 10:25 on the bottom right corner of the screen. Okay, so the initial momentum is clearly 0 plus, in this case, there's no force, there's only a moment, so 0.9 t square dt, the integral goes from 0 to 5 equals r cross mv. R is 0.6, mass is 2 kgs, and velocity is unknown. So 0.9 t cube divided by 3, 0.2 v, 0.1, so that's is it 10.42? No? 31.25.
I don't understand why the moment on the end is supposed to be r cross mv multiplied. Shouldn't, whenever you have a cross, isn't it the magnitude times the cosine times the sine of the angle between them? But I mean, why don't we have that?
Oh, so okay, so the question is, this term here is r cross mv, but the cross means when you do the cross product, it's basically r times mv times the sine of the angle between the vector r and v. So in this case, r is this way, and the velocity is at right angles, so it's 90 degrees. So sine of the angle between the two is 90, sine 90 is 1. So two blocks, each of mass 400 grams. Two blocks, each of them have a mass of 400 grams. The blocks are fixed to the horizontal rods, and the initial velocity along the circular path is 2 meters per second. If a couple moment m equals 0.6 Newton meters is applied about CD of the frame, determine the speed of the block when time t equals 3 seconds. The mass of the frame is negligible and it's free to rotate about CD and neglect the size of the blocks. Okay, so again, similar idea. Things are spinning in circles, and they're acted upon by a force, a moment in this case m. It's going to speed up. We're going to figure out what's the speed in 3 seconds. So again, HO plus principle of angular impulse momentum. Okay, only because things are spinning in circles, and if we use this principle, we'll get rid of some of the forces, specifically the forces which keep that rod, the vertical rod, standing in that position, right? So those forces will not appear in the equation. M0 dt T1 T2 equals H0 okay, so let's see, we're given the initial velocity, it's not 0, it's 2 meters per second. So we need to find R cross MV. So let's do that for each of those two blocks. Okay, for B, R is going to be this. It always points from the center to block B. The velocity is as shown, it's to the right. So again, if you do R cross MV, which is simply, that's R, this is V. Okay, if you curl your finger from R to V of the right hand, your thumb gives the direction of the moment. It's going to point upwards. So let's assume that upward direction is positive. So this is going to be R times MV. This is for MVR, and that's for block B. Let's do the same thing for block A. So for block A, the vector is pointing from the center to block A, so that's going to be the direction of R is that way. Velocity is, I switched it. Let's put B. Yeah, I'll move that. Hold on. Yeah, I'll do that. RA, and since the V is this way, I'll move it. Okay, so now we are set to do R cross V. So again, if we do R cross V, curl my fingers from R to V, the thumb gives the direction of the moment, and it's upwards, just like this one was upwards. So both of them would have a positive sign. This should have been, this is right, this is B and this is A. So it's really, we don't have to distinguish between the two because A and B have the same mass, R is the same. So this is really 2mVr plus the external moment. Okay, in this case, the external moment is, you got to curl your fingers along the arrows, and your thumb gives the direction of the moment, it's upward. So it's positive. Now, if I switch the sign, if I had shown the moment this way, then again when I curl the fingers, I curl them this way, my thumb gives is downwards, so it's negative moment. This is positive. So m is 0.6 dt. T goes from 0 to 5 equals, when I do R cross MV, I have the same logic, right? It keeps going that way. So it is going to be simply 2mVr, but this is at t equals 5 and this is at t equals 0. What's that? T equals 3, sorry, t equals 3. Okay, so 2 times mass, which is 400 grams. Velocity is 2. The radius is 0.3 equals, plus. Since the torque is constant, simply 0.6 times the time difference, 5 minus 0. So 0.6 times, this should be 3, So 0.6 times 3 equals 2 times 400 divided by 1000. V is unknown, R is 0.3. So one equation, one unknown. V comes out to be 9.5 meters per second. Okay, any questions? Any questions? A 4 lb ball B is traveling around a circle with radius is 3 feet, okay, with a speed of 6 feet per second. If the attached cord is pulled down through the hole with a constant speed 2 feet per second, determine the ball's speed when the instance r equals 2. So some point of time the radius is going to be 2 feet, and you got to find the velocity when the radius is 2 feet. Initially, you're given that the velocity is 6 when the radius is 3 feet, and you got to also find the work done in pulling down the cord. Okay, so it's pulled down, because of which the speed is going to change. So principle of impulse momentum, h01 plus m0 dt equals h02, where 2 and 1 are the instances before and after, so we're 3 feet and 2 feet. Okay, now in this case, assuming there's no friction, the only force which is pulling the ball is the force which is inwards towards O. Okay, and what's the moment due to that force? 0. So the moment is 0. There's no other force, there's no friction. So if there was friction, yeah, there would be a force, but no friction. So we get h01 equals h02. This is actually called another principle. It's called the principle of conservation of momentum. Well, specifically angular momentum. Right, so if you remember last class, we talked about principle of conservation of linear momentum. Like there's a block, a bullet penetrated and moved at one system. m1v1 equals m1v1. So mivi initial equals m2 mfvf, the final momentum. So that's similarly you have this principle, but it's for the angular rotations. So given that, let's try to write the individual quantities. R1. So R is, we write here, R is pointing from the center towards the ball B. The ball has a velocity in this direction. Okay, it also has a velocity in this direction, VR. Because it's being constantly pulled inside. So when I write R cross MV, I need to find the contribution due to R cross MVB plus R cross MVR. Okay, now VB is that way and R is this way. So when I do R cross VB, I will get, my thumb will point that direction, so it's going to be negative, assuming upward is positive. So this is negative MVR. VR is this direction, R is that direction. So when you do R cross VR, what's that going to be? R is pointing this way, VR is pointing that way. So when two vectors are aligned, the cross product is always 0. Because the sine of the angle between the two is 0. Sine of 0 is 0. So this is 0. Okay, so we can put that here, minus mv r, and that's initial equals, a similar explanation applies when it moves inward. So r, you get minus mvr, but v instant 2. So the masses cancel off, they do not change. The velocity is 6, the radius is 3, equals the new velocity, which is unknown, and the new radius is 2. So from this we can solve for velocity. It is 9 meters per second. So it's 9 feet per second. Okay, one last thing and I'll let you go. We also told to find the work that has to be done to pull the car down. One way to find the work is if you find F, the force F which I drew there, and the displacement, then I can find the work done. But that's the longer route to do it. A shorter route is we can use the principle of work energy, which states that the initial kinetic energy plus U12 equals T2. We are trying to find this. We know the initial kinetic energy, we know the final kinetic energy. The initial kinetic energy is half